Good day, everybody, and you're almost welcome to this Saturday's CNPS technical session. Today is the 28th of February, 2026, and today we're very happy to have a gentleman who actually has been quite prolific in his publications, because I've been looking at some of them. Musa Abdullahi, I think there's a shortened form of his name, maybe Musa Daji. I think he's using that. Yeah, a bit easier for us to pronounce. So Musa, as far as I can see, because I've had a look at some of his papers, he's got a very analytical mind, which is something that's after my own heart. And he's looking at the introduction of a velocity factor in Coulomb's law. You see, as far as I can see, normally when you express the Coulomb's law, you don't get this factor. There might be a V in there. And this gives rise to expressions of C plus or minus V later on, which in a way is a bit of heresy to conventional ideas, where you're not allowed to add any additional speed to C, the speed of light in vacuum. So Musa's summary is basically a velocity factor in Coulomb's law of electrostatics and also Newton's second law of motion, very interesting, are sufficient for electrodynamics. So that's quite an interesting statement. So he's presenting and a very short summary, because the paper will go into great detail in that. Now, before bringing, I see people are coming in, which you're all very, very welcome. I'll just tell you what the situation is. After a couple of administrative matters, I shall bring Musa up onto the stage, and I shall also bring his paper up. He has quite an interesting paper, and he'll be going through that paper and explaining things. Now, the format normally is that Musa, or our speaker, goes through the paper, and then when he's finished, he actually also has slides. He's made, I think, 5 slides, and I'll put those up because they're sort of a summary of the main tenets that he's talking about. And then we'll be able to address some of the questions. Now, people coming through on the social media are invited to put questions up, and I see David Bauer has just said greetings from Southern Florida, which is fine, and greetings back to you, David. But if you have a specific question, please put question for Musa so I don't miss it, because I might miss it otherwise. And I'll put that question to him and he'll be able to deal with that. The other thing, Musa actually has a number of colleagues or even members of his family there, so they might be chipping in as well, and they're all very welcome. We have a number of people in the green room. I see some of them have come in already. So we have some regulars, and we'll be bringing them in later. And the people in the green room can come in and they can have a one-to-one chat with Musa. So that's it. And I always say this, although I don't think it's arisen during my tenure, that if there's a very, very urgent matter, it would be possible to interrupt the speaker. Now, that's something we'd avoid doing unless absolutely necessary. But if somebody says, "Look, that's a major thing. I don't understand what he's talking about," we can interrupt Musa and we can maybe ask for his response. But failing that, we can put any questions to him after the session, and he'll endeavour to deal with them directly. Okay. So just before getting down to the I hope I haven't been sharing too much, because I've stopped sharing now. So just before getting down to the main thrust of today's meeting, I'll just play a little video. It only takes 1 minute, just about the funding mechanism. We've been doing this for the first quarter of this year. Actually, I think we'll be doing, I thought we'd be stopping it on the 1st of March, but I think we'll probably stop it on the 1st of April. So we might be playing it January, February, March, because it's just an endeavor to try to make up the shortfall between the income to the CNPS, basically from the membership dues, and the running costs, which actually exceed the membership income. So, and I think we've certainly reached more than 50% of our target. So it'll only take a minute. I'll just play it now, if I may. it's the president of the CNPS, David de Hilster, addressing us on this matter.
Hello, everyone. I am David D. Hilster, president of the CNPS, and this is our annual fund drive. First, I want to thank all of those who have been paying their annual and monthly memberships through our automatic membership system. It is greatly appreciated. Since 1994, this group has been pioneering support for critical thinkers outside of mainstream science, and we continue to do so through our virtual presence, through our Saturday morning live streams, and our website discussions. Since last year, we have cut our expenses down to something reasonable for our current membership. In 2026, we hope to implement the Discourse Discussion Group as our primary discussion software. Our current website system, in my opinion, is not ideal. We hope to change that. To donate, you can go to fund.naturalphilosophy.org and donate whatever amount that works for you. Your contributions are greatly appreciated. Thank you.
Very well. Well, the main important aspect of what we're doing is our discussions, such as the talk today. But obviously, there are practical things in daily life, and we do need some money to keep the servers running and so on and so forth. So let's hope we can achieve both of those. Now, Musa, I've been speaking to Musa for about 20 minutes, so we know each other, and you're very welcome again. We're delighted to have you. And so what we've agreed is that I have the controls here. It might be a bit quicker, and I can put up Musa's paper. I've brought it down now, but I can put it up. So what I'll do, with your permission, Musa, is I'll give you the floor now. I'll remove myself. I'll give you the floor. You can say a few words of introduction if you wish about yourself, your experience, how you got involved in this, what you're hoping to do. And then just tell me, say, Ian, put up the paper now, please, and I'll do that. Is that all right?
Thank you, Ian. Yes.
Very good. I'm going to disappear. The floor is entirely yours, Musa.
Ladies and gentlemen, good afternoon. You are welcome to this session. My name is Musa Abdullahi. I'm speaking to you from Kaduna in Nigeria. Can we have the slide number 1, the abstract of the paper?
I'm just coming back because it'll take me a moment just to put it up. So just
slide number 1.
Ignoring it. So I have to share my screen. I thought what I did previously would have been retained, but I have to do it again. There's no problem. Entire screen. Now I have to bring up share. I have to bring up your abstract or your paper. Here.
Slide number 1.
Okay. I just want to make sure that it's all right now. It's the talk itself. Is that all right? Is that it? Can you see it? Can you see it there, Musa?
There's a paper, yes.
Okay. Right. Well, I'm going to let you continue. If you need me to, I think you're hoping to bring up the slides after you finish the paper. But if you want to refer to anything, or
as I go through the paper.
So it's all right what I'm doing now, is it?
Can I have slide number 1?
Now, when you say slide number 1, you mean the other file, do you? So
MPA slides.
So let me check. The slides, are they the slides there?
Yes, that's correct.
So I'm on slide 1 now, am I?
Yes. Okay.
So if you want me to scroll down, just say so.
Okay, I can scroll from here.
Shall I scroll?
Zona. I can begin now.
Yes, please do so. Yeah, please do so. Yeah, it fits on one
Yes.
page.
Okay. Just
Just
as a prelude, you can start by saying that the problem of physics today lies in making Coulomb law independent of speed of the charged particles. Once you put a velocity factor in Coulomb's law, everything comes to light. The paper inserts a velocity factor in Coulomb's law of electrostatics and equates it with Newton's second law of motion to obtain speed of light c in a vacuum as the limit to which a charged particle is accelerated by an electric field at constant mass as the rest mass. The force on an electric field is transmitted with velocity c minus v relative to a charged particle moving with velocity v, where c is velocity of light in a vacuum. This automatically makes velocity c a limit whereby the force cannot catch up and impact on the particle. For a charged particle moving with velocity v relative to an observer, the electric field is increased to account for the kinetic energy without any increase in mass. Force on a moving charged particle is less than the force on a stationary one. The difference is radiation reaction force. Oui.
She's scrolling down.
Nani ke scroll? Nani ko?
No, you can't scroll down. See me to my again, you're scrolling down.
Can you scroll down, please?
you scroll down. Yeah, just tell me to do that. Yes.
Okay.
Your hair, I think, at the moment.
Force on a moving charged particle is less than the force on a stationary one. The difference is radiation reaction force, something similar to frictional force, against which work done appears as radiation. Radiation is obtained from accelerated charged particles outside quantum mechanics. Gravity, it explains, as a force of attraction between the masses of charged particles in a body, according to Newton's law, while the electrostatic forces of repulsion and attraction, according to Coulomb's law, cancel out exactly everywhere. An electron attaining the speed of light with constant mass should bring a lot of relief to physicists. I can go to my paper now. Start with the introduction.
Paper now. Okay. Is that all right?
Yes.
Introduction.
Newton's second law of motion was enunciated in 1687 by Sir Isaac Newton. This man is certainly the greatest mathematician and physicist of all time. Newton's law of motion formed the foundation of classical mechanics. Coulomb's law, enunciated in 1787 by the French physicist Charles de Coulomb, is one of the most important principles in physics. The theories of general relativity enunciated by the celebrated physicist Albert Einstein, and the quantum theory originated by Max Planck are the reigning doctrines of physics today. However, these theories are not mutually compatible. So one or all of the theories may be wrong. This paper, invoking aberration of electric fields, a missing link in physics, aimed to introduce radiative electrodynamics, where a charged particle is accelerated by an electric field at constant mass, the rest mass, with emission of radiation. Radiation is the difference between change in potential energy and change in kinetic energy of an electron or a charged particle accelerated by an electric field. Radiation reaction force, like a frictional force proportional to velocity in an electric field, prevents accelerated charged particles from going beyond the speed of light. So really, we should not say that particles cannot reach the speed of light, only that they cannot go beyond the speed of light. Electrons are easily accelerated and have been accelerated to the speed of light. Coulomb's law. Can we go to?
Shall I scroll down a little more?
No, the slides.
Oh, you want to go to the slides, do you?
Yes.
Yes.
Scroll down. Yes. 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 This is this. Yeah. Is that okay? That's okay. This figure 1 illustrates Coulomb's law. As I said earlier, the greatest problem of physics today in making Coulomb's law independent of speed of the charged particles of a charged particle in an electric field. The expression here gives Coulomb's law between two charged particles, K and K, Q and K, separated by a distance R in space. We go to the next.
Here?
Yes, yes. Okay. Newton's second law of motion relates the rate of change of velocity at time t, that is acceleration of a body of mass m, as F is equal to mass times acceleration. It's a very important principle in physics. Now, with the coming of relativity, where mass is supposed to increase with speed, Newton's law was changed to force is equal to the rate of change of momentum, where the mass is not constant. Now, if we consider an electrical force as due to impact of electrical force at the speed of light, an electrical field hitting a charged particle at the speed of light can only accelerate it to that speed. If an electrical force is transmitted at the speed of light, an electrical force can accelerate a particle only to that speed and no faster. It's just like a sailing boat. A sailing boat cannot go faster than the speed of the wind propelling it. So if an electric field is transmitted as the velocity of light, that field can only accelerate a charged particle to that speed and no faster. And this is exactly explained more precisely by aberration of electric field. Aberration of light, as we all know, is a phenomenon discovered as far back as 1978 by Reverend Bracely. This another related phenomenon is aberration of electric field. The figure here, figure 2, explains aberration of electric field. Aberration of electric field is a phenomenon missing in physics. Aberration of light clearly demonstrated the relativity of speed of light. Aberration of light is now discarded, it's an abeyance, because it contradicts the principle of constancy of speed of light. This is most unfortunate, because with the absence of aberration of light and aberration of electric fields, some other principles have to come in. Relativity came in, special relativity came in to explain why a charged particle cannot be accelerated beyond the speed to the speed of light. Quantum mechanics came in to explain emission of radiation from accelerated charged particles. If you look at figure 2 here, a charged particle moving with velocity v experiences the force coming at an angle alpha, the aberration angle. On this basis, we can express the, can you scroll up?
Scroll down.
Up then.
This way?
Go on. No, go to, sorry, go to number 3, down, yes.
3, yeah. Some people call
Okay.
Jan what others call up.
Okay, go on, yes, there.
Here.
Now, on the basis of aberration of electric field, the force on a charged particle is shown here. I hope you can all see it under figure 2. We have an expression here for the force on the charged particle. The force depends on the angle theta between the instantaneous line joining the two charges and the velocity. If you look at the equation under slide number 3, the charged particle can move with theta is equal to 0, that is with acceleration. It can move with theta equal to pi radians, that is deceleration. If it is a negative charge, if K is a negative charge, it may also move with theta equal to 5/2 round the charge. So actually the equation here under slide number 3 is the real equation, where you can immediately see if C is equal to V, yes, if C is equal to V, the force reduces to 0. there is no need for an infinite mass to prevent a charged particle from going beyond the speed of light. What should happen is that the accelerating force becomes zero at the speed of light. While the accelerating force is zero, the force, the velocity or the speed remains constant according to Newton's laws of motion. Where there is no force, the velocity remains constant. And the equation under slide number 3 explains that there is no need, let's say again, for any mass to increase to an infinitely large value. What is an infinite mass anyway? An infinite mass is the mass of the whole universe. How can that be contained in a laboratory? It is unfortunate that the theory of relativity shows mass as the independent variable rather than force. It is much easier to have force reducing to zero in order to give a constant ultimate speed than to have mass increasing to infinity in order to reduce speed to a constant value. So the problem with relativity is that really the infinite mass is a very uncomfortable situation. We know there can never be an infinite mass anywhere, but there it is. As far as relativity is concerned, a lot of the experiments, even the experiment with Bartolozzi linear accelerator, the electron there reached 0.99 of the speed of light. For all practical purposes, that is the speed of light. But we cannot say that a particle has reached the speed of light for fear of arriving at infinite mass. So all we should say is a charged particle like an electron cannot be accelerated beyond the speed of light, but can be accelerated to the speed of light, as long as we do away with the issue of infinite masses. All these problems with special relativity, quantum mechanics, even general relativity came because of lack of this velocity vector in Coulomb's law. Of course, under the present system, there may be no need to look at old issues like Coulomb's laws and so on. But really, we need to go back to the fundamentals if the present situation becomes intractable. And I say that the issue of special relativity with infinite mass is a very uncomfortable situation. So any idea of mass remaining constant, at the same time, the speed of a charged particle reaching the speed of light with constant mass should be welcomed. Even the speed of the protons in the Large Hadron Collider have reached the speed of light, but there was no infinite mass. Here is a very relieving situation to have speed of light without infinite mass. And all this came because of neglect of operation of electric field and operation of light. The relativists, those who profess on the theory of relativity, maintain that operation of light does not apply on terrestrial settings in the world. Just begging the question. Conveniently forgetting that Reverend James Bradley made his discovery in a monastery some 10 miles away from London. What led to the neglect of the operation of light was simply the force and the predominance of the theory of relativity. We are almost in a situation now where you dare not challenge it, but it has to be challenged sooner or later. And this paper is proposing that the constancy, the speed of light being a limit, is simply the result of accelerating force reducing to zero at the speed of light, rather than mass becoming infinite at the speed of light. And the equation here under slide number 3, you can use it to obtain an expression for the speed with time for accelerated motion, for decelerated motion, all of which reach a limit equal to the speed of light, with mass remaining constant as the rest mass. I say it again, the problem of physics is in neglecting operation of electric fields. Operation of electric field happens if an observer like astronomer, like James Bradley, moving in light. Operation of electric field comes if a particle moves in an electric field. Both light and electric fields are propagated at the speed of light. So if you have operation of light, you will also have operation of electric field. Putting into abeyance operation of electric field led to so many things. There can never be a vacuum in science. Somehow, somewhere, some clever person will find an expression or a reason for this or that. So in the absence of operation of electric fields, it became necessary to introduce special relativity to explain the speed of light being a limit. It necessitated the introduction of quantum mechanics to explain emission of radiation from accelerated charged particles. Here, what we are saying, as far as radiation is concerned, if a charged particle is accelerated by an electric field, the accelerating force at a given velocity is less than the force on a stationary charged particle, and the difference is radiation, the reaction force. It is emission of radiation which prevents charged particles from going beyond the speed of light. But at the speed of light, the accelerating force is equal and opposite to the radiation reaction force. With no force on the particle, it continues to move with constant speed of light. Can we go to the next slide? Yes. Now, yeah, it's okay. Speed of light aberration refers to a particle moving in an electric field. We also have aberration with respect to a charged particle moving relative to an observer. Now, this is an issue which has really never been treated properly in physics. What is the velocity? What is the electric field of a charged particle moving at a velocity relative to an observer? Figure, can you scroll up again?
This way.
Yes. Sorry, up.
Yeah.
Up. So, okay, down, maybe. Down. Yes. Go on. Okay. Now, this figure is really very instructive, very interesting. If an electric charge Q moves with velocity V, the electric field becomes what is put here as EV. The electric field is shifted by an aberration angle alpha from the electrostatic field. Can you go up? Yes. Sorry, down. What is down?
It's just different terminology.
Okay, that's okay. That's okay, yes. Now, if an electric field is moving, if an electric charge is moving with velocity V, the electric field becomes EV. It is increased in the direction of motion and decreased backwards. In the overall, there is an increase in electric field. This increase in electric field accounts for the kinetic energy of the moving charged particle. The mass remains constant. It is the electric field which increases. And if you take the energy of the electric field, the increase of energy of the electric field is equal to the kinetic energy of the particle. So you can explain increase in energy of a moving charged particle, not by change in mass, but by increase in the electric field. And if you work out the electric field, you equate it to it becomes equal to the kinetic energy with constant mass. So it is increase in the electric field which accounts for the kinetic energy of a moving charged particle, not increase in mass, but increase in the electric field. If you look at the equation under figure 3 here, you can make CV in the direction of motion, in the opposite direction of motion, or perpendicular to the direction of motion. If you put V is equal to C here, if a charged particle is moving at the velocity of light, the velocity, the electric field in the direction of motion is doubled. The electric field in the backward direction is reduced to 0. And somewhere in between, the electric field changes. In the overall, there is an increase in the electric field to account for the kinetic energy, while the mass remains constant. That's why figure 3 is very important. And should be noted, please, because it is a new presentation. The electric field of a charged particle moving with the velocity b increases. It is the increase in the electric field that accounts for the kinetic energy. The mass remains constant. Can you scroll down? Yes, 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 it's enough. It's enough. Now, under figure 3, there's an expression for dynamic electric field. If you substitute for the angles theta and alpha, as indicated in the figure, you will get the electric field for motion, for in the direction of motion, electric field in the opposite direction. And this explains quite a lot. Can you go down again? Now, yeah, it's okay, it's okay. We all talk of electrons, positrons. What are they? We know their masses, we know their electric charge. What is their shape? If an electron or positron can assume any shape, it is most likely to be a spherical shape, a spherical shell of a given radius. And that radius should be the smallest length in nature. So if you look at the figure here, we have the speed of light as given by Maxwell. Can you move down? Yes, yes, yes. You can calculate, you can derive the intrinsic energy of a charged particle, E squared over 8 pi epsilon A. This is a very well-known classical formula for the energy of a spherical shell as a charged particle. You can derive an expression for the mass of the electron or positron in terms of the charge, mu E squared over 4 pi. This is an expression for which I have been accused all over the place that it cannot be right. But nobody has proved me wrong. Expressing the mass of a charged particle in terms of the charge and the radius is a spherical shell of radius A. If a charged particle can have mass, and we all know it has mass, and that neutral bodies are made of an equal number of negative and positive charged particles, that is electrons and positrons. A neutral body is made up of an equal numbers of electrons and positrons, which have mass. The electrostatic forces of repulsion, and attraction cancel out anywhere. Let me say that again. The electrostatic forces of attraction and repulsion from the charges in a neutral body cancel out everywhere in space. Exactly. But the gravitational forces remain because these huge charged particles have masses. And as such, they have gravitational force in accordance with Newton's inverse square law. So really, there is no need for general relativity to explain gravity. In any case, if you look at general relativity very well, there is no way it can make the apple fall down. It is more likely to make the apple go up. Let me repeat myself here again because it is the crucial part of my paper that a neutral body is composed of an equal number of positive and negative charges, an equal number of electrons and positrons. The electrostatic forces of attraction and repulsion from two neutral bodies cancel out. Exactly. But the gravitational force of attraction between the masses of the charges remain. This should be a better explanation of gravity than carving or warping of space-time continuum in general relativity. And I think this really is the crux of my paper in explaining gravity outside general relativity in accordance with Coulomb, in accordance with Newton's law. Whatever you do about gravity, you have to come back to Newton's inverse square law. If it doesn't explain Newton's inverse square law, it's simply speculation. Of course, as scientists, we are allowed to speculate in any way we wish. Whether it is correct or not is a different ballgame. But I think we here have a better explanation of gravitation in accordance with Newton's law than offered by general relativity. General relativity is a very interesting, very attractive proposition, but it has no reality. I go to the conclusion of my paper.
Do you want to go back to the paper now?
Huh? No,
Yes.
I have the conclusion here. I have it. I will read it from here.
Okay.
Yes. Explanation of gravity, I have already mentioned it. Gravity is due to the attraction of the masses of electrons and positrons composing neutral bodies. I also explained inertia. If you go back to slide number 3, can you go back to slide number 3?
Is that where I am at the moment? No. Is this slide 3?
Yes. No, go on. Yes, this one is okay.
Okay.
If you accelerate a charged particle to generate an electric field, in the opposite direction of acceleration in accordance with the law of electromagnetic induction, Faraday's law of electromagnetic induction. If you accelerate an electric field, regenerate an electric field in the opposite direction of acceleration. Now, this electric field is a reaction due to acceleration. It's a reaction of acceleration. To every action, there is an equal and opposite reaction. That's Newton's third law. The induction electric field is here indicated as EA. This electric field acts on the very charge producing it. It produces the inertial force. So if you multiply the value of the charge producing the induction electric field with the induction electric field, that will give you an expression for the induction force. If we are able to explain gravity, we are able to explain induction, we have come a long way as far as physics is concerned. Conclusion. In view of operation of electric field, the paper has added a velocity factor to Coulomb's law of electrostatics, and also added Newton's second law of motion to introduce radiative electrodynamics, which is sufficient and applicable to all particles at speeds up to that of light, with mass remaining constant. Recommendation. My humble appeal here is that aberration of electric fields, a missing link in physics, and aberration of light, discovered as far back as 1728, should be reinstated and recognized in physics, particularly aberration of electric fields. I think the world has not done justice to Reverend James Bradley for discovering aberration of light. This should be remedied to bring back physics on the right course. As we are here now, we have plunged physics into the wilderness of special relativity and plunged it into the quagmire of quantum mechanics. Quantum mechanics and general relativity are very attractive propositions, but they need to be re-examined. And this is what this paper tries to do. And we strongly recommend that the issue of operation of electric field is covered by Reverend James Bradley. After 30 years of meticulous measurements and observations, should not be thrown away. Aberration of electric field is hardly mentioned anywhere in physics today, but it is a vital factor in physics. So is aberration of electric field. This paper is short, but the reference below is to a much wider paper, which contains more copious arguments as to why we should revisit the theory of special relativity, quantum mechanics, and general relativity. They are very brilliant propositions, very attractive, but they lack reality. Let's say reality needs to be examined. And by saying that any phenomenon in nature has a physical explanation, and a mathematical expression subject to experimental verification. Anything that does not conform to reality needs to be just taken as it is, not real. Nature is simple and wonderful. Once you unravel nature, you will be astounded at its simplicity and beauty. All these beautiful theories are just there to provide teaching materials, examination materials, and so forth. But we need to re-examine them. Distinguished ladies and gentlemen, I rest my case. I will be prepared to answer questions, please.
Okay, so that's the end of your formal presentation, is it, Musa? I might bring down these papers and slides. We can bring them back again if you need them to answer any specific questions. But let me try to get things back. And the participants will have to forgive me because I haven't been looking at the questions coming in because I've been just projecting things. So if you give me a moment, I'll do that. Let me stop sharing my screen first. Let's see now, how do I do that? Here we are. Stop screen. So I think things should be back to normal, and we should have our two videos there. Let me just, if it's all right, what we normally do, Musa, is we just scan through the questions, and you might be able to answer them, pretty quickly. The more detailed discussion which will arise when we bring people up from the green room may require a bit more information. Actually, perhaps I sometimes do this. I take the opportunity, since I have the honor of hosting this, maybe of popping the first question. So maybe I can do that just to start things going. Actually, I will say that I found this very, very useful for my own part, because I've read Musa's papers, and they're quite turgid. I mean, that's a compliment. You know, all these academic papers, if you haven't been working in the area yourself, they can be a little difficult, a little heavy. But I found them interesting. But I found his talk now very, very illuminating. He spoke slowly and he described things very, very well. And it was very useful for me, having read the papers in the first place, to have that. So maybe, and you know, I found the whole business. Why haven't they introduced this speed factor or velocity factor into Coulomb's law? It seems so obvious. And this whole question of aberration coming from Bradley's first observations, applying to everything. But and the whole question of maybe getting an explanation to gravity when the charges balance out and so on, and the the radiative reaction and all that. All most fascinating. I'm going to look at this in more detail. But just one maybe question, which is just putting it out a bit, Musa. The aberration arises because of the finite speed, and we know that light has a finite speed, and there's an aberration. And I don't have any problem if you have a moving charge. Of course, it's moving at speed v, and therefore there would be some aberration. And you've worked out the theoretical results there, and you have them in the equations. But if fields interact at an exceedingly great speed, almost instantaneously. So to give you one example, Tom van Flandern has given some evidence that gravitational speeds, the gravitational fields establish themselves at almost infinite speed. We needn't say infinite speed, but maybe it's orders of magnitude greater than the speed of light. So therefore, it appears that there's no gravitational interaction. You can observe maybe at the time of a total eclipse of the sun that the gravitational field establishes itself pretty instantaneously relative to the way the light does. It's delayed by 8.3 minutes. So my question is this. I thought maybe there was some evidence that electrostatic fields establish themselves pretty instantaneously at a much, much greater speed than the speed of light, orders of magnitude greater. And therefore, as distinct from moving charges, the electrostatic field itself shouldn't show aberration. What would you say to that?
Gravity is transmitted at the speed of light, not at an infinite speed. So if the sun ceases to disappear, it will take how much? 8 seconds something before we feel the result.
8 minutes, yeah.
Gravity is nothing can be transmitted beyond the speed of light. Nothing.
Oh, okay. Well, that's something we can perhaps come back to. It's an interesting discussion. I'm glad I got your take on it. So, if you just forgive me, I'm just going through the comments now. Some of these are just wishing you a good day and so on. Well, I actually thought this a bit, but he says you mentioned just en passant. I don't think it was central to your point that say a sailing boat can't go faster than the wind, but Shockwave says you're wrong. Sailboats can go faster than the wind. I think maybe that might be right, but you were only giving that as an image, weren't you?
Yes.
Is it a Bernoulli effect?
We can take this up with the issue of constancy of speed of light according to relativity. Nothing can be further from the truth. There is no way the speed of light can be constant to all observers, moving or stationary. But this is even held by the authority of the propagator, Einstein himself. If I move towards a source of light and I move away from a source of light, you're telling me that the speed of light remains the same? No way. So in one case, it is C plus V. In another case, it is C minus V.
Yeah, that must be right. Of course, it must be right. We're getting a bit diverted now by these comments, but they're interesting. He's just saying that if you're going to high-performance sailboats, particularly those equipped with hydrofoils, such as sail, things, catamarans, can travel significantly faster than the speed of the wind. Some is exceeding it by 3, probably 3 to 1. Okay, it's not what you've just said is central, and I've quoted that Alfred O'Reilly, who wrote this big tome on electromagnetics in the 1930s, says that special relativity says that if you have an observer who's moving, say, at half the speed of light, and a ray of light flashes by him, well, he will observe that ray of light not at half the speed of light, but at the speed of light. And O'Rahilly says quite succinctly that that only not seems to be nonsense, but actually is nonsense. So I think
correct.
most people here would agree with you.
It's
that.
only the authority of Einstein that is keeping that alive. That is keeping that nonsense alive.
Yeah.
Because the authority, the influence of Einstein is so much. And yet, if you compare Einstein with Newton, you will say that Einstein was not educated compared with Newton. And look at the influence that he now has on physics. I repeat that again. If you compare Newton with Einstein, I will say that Einstein was not educated. All these thought experiments. What is a thought experiment?
Yes.
You can perform an experiment or no experiment. There's nothing. The experiment can lead you to a lot of problems. And it has led us to a lot of problems. Einstein was a personality of the mass media. He was promoted by the mass media. But if you look at it properly, Einstein is nowhere near Newton. And yet, the amount of adulation showered on Einstein is now beyond imagination. It has taken over physics, forgetting those who really were the founders of physics. Newton, Galileo. Galileo is another one the world has really not done justice to. Maxwell. Maxwell is far greater than Einstein. You will never hear Maxwell or Newton making a statement just like that. E is equal to mc squared. How? How? I have never seen any proof. I have been a student of physics, a teacher of physics, and now, what will I say, an independent researcher. I have never come across a convincing proof of E is equal to mc squared. I have proved on 3 occasions that E is equal to a half mc squared. And I hope that before I die, that proof will be recognized. In the longer paper I have indicated 3 proofs of the equation that E is equal to a half mc squared. If you say E is equal to mc squared, it presupposes that a particle can move above the speed of light. This is
I found your explanation about
day.
the force, reducing to zero rather than the mass becoming infinite, because it's blowing up, as you yourself basically were showing. The whole equation was blowing up. And also a question, if I may, just on what you just said, Einstein's publicity and so on. We're so well known and thought to be the greatest brain ever, and actually they as you know, I'm sure, Musa, they've propositioned people in the streets of Edinburgh, where Maxwell was. They'd never heard of James Clerk Maxwell. Most people.
Yes.
By the way, Musa, we have a chap here. I know Kev Cowan is more of a mainstream person, and so this is a frequent argument. People say they say, well, we put a man on the moon, so I think physics is on the right course. I think what he's saying is that generally accepted physics, the things that maybe you and I and others would be attacking every day, um, that is incorrect to attack them because we put a man on the moon. So I don't know how you'd answer a question like that.
No, you can have advanced technology without mathematics. Mathematics helps. All the technologies in the past on which we are benefiting today were not based on any science. So you don't have to have all these high sounding equations before you have advanced technology. It helps, yes, but it's not necessary. If anything, a lot of the equations we have these days need to be re-examined. See, in our case, if I may say so, you may not see the need to re-examine all these paradigms because they have a stake in its continuation. But somebody like me maybe will have the inclination to re-examine what is being done. Mark you, I get more criticisms from my fellow Nigerians. Hardly any Nigerian read any of my papers. All the requests, all the comments I get were from overseas, UK, America, Japan in particular, but hardly any from Nigeria. So
well,
it's
I'm
not
the same. I'm an Irishman, and Irish people don't comment on my papers at all, except maybe the odd criticism thereof. So we're both in the same boat there.
No, not for different reasons. They may not for different reasons. But in my own case, it is most saddening. Not a single university in Nigeria has called me to say, come, Musa, talk to us about this rubbish you are talking about. None. For example, I went to university in the UK. Maybe there's a little bit difference. But I also attended a university in Nigeria. I taught in a university in Nigeria. And it saddened me very much to see that not a single Nigerian university has called me to say, Musa, come and talk to us this rubbish you are talking about. So the fact that you have invited me to give a talk really makes me very grateful. If maybe this will expose some of the things one has been doing.
So this is what the NPS is all about. I mean, we're slowly trying to chip away at ideas which in the past have not been subject to objective consideration. And we're delighted to have people with different takes on physics, on analyzing, on critical thinking physics, people from different parts of the world. I mean, I might even say that the society is rather dominated by the USA, and that's great. I mean, Chappelle was an American and so on. But if you look at the map, actually, of people participating, dissident physicists, or even people like Kev here, who's interested in physics but doesn't agree with a lot of our views, we're all over the world. We have thousands of people, I think 2,000 or something. So certainly for my part, I'm always delighted to have people. Well, we've had quite a number of Europeans, but I'm interested in people from Nigeria. As I said to you earlier, the second person, we had Akinbo Ojo, who gave us some good presentation some months ago, and yourself. We're delighted to have that. And we're also looking for people maybe from Southeast Asia or the Southern Hemisphere. So we're delighted to have you, and thank you so much. Now, I'm just forgive me. I have been looking at the questions, and I've skipped a lot. Yeah, okay. So Yeah, we could get into that philosophical problem. Let's just see. There have been a couple of private chat things. Ian, can you magnify the paper so text fills full screen? I'm sorry, Jim. I didn't see that until now because I was sharing the thing. Aberration question about. Okay, we'll bring all of you in a minute. So first of all, what I might do, Musa, is if anybody in the green room has an urgent wish to contribute or discuss things with you, he could put up his hand and I'll bring him in now.
Okay.
If he doesn't, I will invite most of you to come in because, okay, there's nobody at the moment putting up his hand. We have half an hour left, but James Keane has raised these points, and I apologize, Jim, that I've missed your point. I hope you could read the paper, but he's gone. Where's Jim? I think he can hear me, but I think his. Let me see now. Jim is gone. We might bring him back in a moment.
Okay.
So, yeah, I'm going to bring Ido in a minute because he has a question about equals MC squared. He's put that in, and thanks, Ido, for that. But let me there's one other point which has come in by Dennis Allen. I think he's not in the green room, but he's made it a point about the equals MC squared. Dennis is not here on the green. So let me put his thing up.
What's a familiar name?
Dennis says, equals MC squared. Since you emit the electrostatic field energy of electrons and protons, that is also equals MC squared over 2. Is that similar to what you were claiming, Musa?
Beg your pardon, please say it again.
I don't know. Can you read it here? E equals MC squared.
Uh-huh.
Since you omit the electrostatic field energy of the electrons and proteins, that is also MC squared over 2. Is he saying there's a contribution of MC squared over 2 by electrons and protons?
Well,
Do you see? I didn't put this up. It may be relevant to what we're looking at now, Musa, but KevCon said E equals MC squared has been verified experimentally to great precision. Now, I was interested in your point that you say, well, it's really equals MC squared over 2. I think that the experimental evidence seems to indicate that E equals K MC squared. Now, the problem is to find what that factor K is. And the first, well, this is my own research, and you may wish to contradict it. The first experimental measurement or attempted measurement of that was the Cockcroft-Walton experiment of 1932, which transmuted lithium into alpha particles by embodying them with high energy protons. And it found that E, the energy, the difference in energy was roughly equal to MC squared. Now, it was claimed that that was the first experimental verification of E equals MC squared. But personally, for my part, I would say no. It indicated that E was of the order of MC squared.
that's correct.
Do you agree with that?
If you should have some theoretical means of proving that E is equal to MC squared, including, of course,
Magic.
experimental verification. I have never seen any proof of E is equal to MC squared. All you get is blah, 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 so E equal to MC squared.
Okay, well,
I think E is equal to MC squared by the increase in electric field of a moving charged particle. You can prove E is equal to MC squared from the inertia of an accelerated charged particle. We can prove E is equal to MC squared from the electrostatic energy in the electric field.
And this sort of relationship, again, it isn't actually due to Einstein. Newton talked about it as well. And you have people like Hassenhurl in Germany, and more recently you had, I've forgotten the man who actually. So it actually predates Einstein. It's not something which he brought in. This,
It did. Yes, it did.
Yeah. But listen, Edo Cal says that it's actually hiding. E equals mc squared is hiding in the nucleus. Now, Edo, who's done a lot of work, he's done monumental work on this whole atomic structure. He's here, and I believe he's audible. He doesn't have a camera, I think. So, Edo, if I bring you up, we don't get your image, but we get your voice.
I hope so. Am I coming through yet?
Perfectly.
Okay, perfect.
So you could you give your take on this E equals mc squared hiding in the nucleus?
Right. So let me just utter a few phrases there and translate it into a question, perhaps. If I understood the presentation right, you're saying E is mc square. I've not seen evidence for that. I think, and that is the first question, that you're relating that to the inertia component, more speed, more mass. However, so is that true? Is that the connection that you're rejecting, if you will? Musa?
No, I'm saying that mass does not increase with speed. Mass of a particle does not increase with its speed.
Right. Okay. I can totally accept that one. The reason I bring up E is mc square is hiding in the nucleus, because when we measure, and for all I can see, these measurements are, very consistent. When we measure masses of elements, of atoms, and we do calculations and stuff, and we look at the energy that is emitted when we fuse, or the energy we have to put in when we fission. This is a historical important example with the formation and the destruction of deuteron, right? From 2 hydrogens or 2 protons, you make a deuteron, or the other way around, you destroy it. Now that is where E is mc square seems to be very appropriate and very accurate and very precise. So from my own perspective, that's why I state E is mc square is hiding in the nucleus. That seems to utterly work. The amount of energy emitted with a fusion process equates the loss of mass for that particular atom. So that seems to work. And then, but then you have the first problem with the inertia and the increased mass component. Now, I already know your position there. What I would like to bring to the table is how to marry the two, if you will. The first one, in the nucleus, we see E is mc square seems to work very lovely. But the other component there, and that is related to the other parts in physics that your presentation was all about, it does not work, or you show otherwise. I would like to bring to the table that there is something of an inherent, or an inherent mass, if you will, meaning the mass of a particle, and the speed component. But I would argue that between brackets, between quotes, big quotes, added mass or added energy, translating to the kinetic energy, if you will, that would be an added on energy component that you, through the formula E is mc square, can express in mass. But I very much agree with you that it would not be actual mass, meaning the inherent mass of the particle, right? It's just an added part to it. I think if we distinguish, if you will, between the added mass and the intrinsic inherent mass, the intrinsic mass is, I think, the term I should use here, then we can reconcile the two, where E is mc squared does work in the nucleus very much, and not so much with the inertia component there. So what I see is that the Coulomb forces work very well in the nucleus, and in the nucleus we have things when we do experiments like kinetic energy, momentum, distinct amount of energies coming off, etc. Do you see your work related to that nuclear physics research / what I've tried to explain right now? Do you see, what are your thoughts about the connection to the nuclear physics in particular? Thank you.
Yes. Thank you very much. my contention is that if you say E is equal to mc squared or E is equal to a half mc squared, it does not mean that M is destroyed and turned into energy. Say, for example, if you combine an electron and a proton and a positron, the thinking now is that they annihilate and turn into energy, gamma rays. The contention is that they don't annihilate. If electron and positron annihilate, there would have been no creation. They would have all annihilated by now.
I totally agree, sir. Sorry for the interruption, but I totally agree. In my book, there is no such thing even as a positron, but please continue. Sorry for the interruption.
Okay, yes. So the mass, the total mass of the universe remains constant. What changes are potential energies and kinetic energies between bodies, into the bodies in space, or charged particles. But they don't annihilate and vanish into thin energy.
Right.
Okay. I just, if I might just put up while we still have Ida there. I've been having some conversation with Kev here, and he just says a recent high precision test of E equals mc squared was conducted in 2023 using Penning traps to measure the mass difference between atomic nuclei before and after nuclear reactions, confirming the equation to presumably very high precision. I think it's washed off here. But do you see, I think some of the work done by Hassan Hurl, whom I referred to earlier, I think he got something like E equals 3/4 mc squared, something like that. And I think the experiment that I referred to, 1932 Cockcroft-Walton experiment under Rutherford in Cambridge, could not distinguish. It wasn't accurate enough to distinguish whether E equals 3/4 mc squared or equals mc squared. But he's referred, Kev has here to some work done in 2023. So I suppose he takes exception to what you're saying, Musa. But
yes,
you've given a very logical explanation of this. Some experiments, which I suppose what are happening in CERN every day, where they're saying, "Oh, the mass is increasing," and you're saying it's not the mass; it's the force. So that's interesting. I have another question here, by the way, from just while we're on this sort of radio electron business. I think it's from Cornelis. He's asking, what did he say? Well, okay, just following on from what Kev says, he says 1 part in 10 billion tested in University of Washington in 2023. So I was wrong. He says, look up these things maybe later. Yeah, okay. Let's find this thing that he was asking something about the electrons. I've missed it now. Oh, here it is. It's a bit of a general question. He says, Musa, how do you define the structure of the electron? You said something about it maybe earlier.
Yes. What I said, if the electron or positron is to have any structure at all, it is most likely to be a kind of spherical shell of a certain radius as the smallest length.
There's Cornelis. He's up now.
Hello?
So that's the man who's asked your question, Cornelis.
Okay, yes. Yeah. You're welcome.
Yeah, basically, I was just asking because you're talking about the mass of the electron not increasing in that, but I was asking because what is like the boundaries between the electron and the electromagnetic field that it's within, and physics nowadays looks at the electron as being just a distortion or a pattern of energy that's focused within the electromagnetic field. And so it doesn't really have a boundary as such. I know that Viraj, Fernando, and Ron Hatch talked a lot about intrinsic and extrinsic energy in atomic structures and that. And that basically accounts for, whether it's focused towards a point to become part of the particle, or whether it's a pattern of energy surrounding the particle, like the pushing force and that, the distortion that causes it to move.
So it's almost conceiving of it as a cloud rather than a concentrated.
Yeah, well, it's kind of more like a pattern of waves, like just dropping a stone in the water, and no matter how extensive that pattern of waves was, as long as it was focused towards that center point in the surface, it would that wave would continue to affect that center point. So it really is part of that pattern is really part of that particle. So when you say that you accelerate that pattern of energy and the mass doesn't increase, what does happen is, like, I think Musa, you said that the field strength around it increased. But in the case of where the particle itself is part of the field and just a distortion part of the field, then what you're doing is you're just redistributing where that energy is and whether it's coherent to a point or not.
Yes, that is possible. But electrons are real, as discovered by Sir J.J. Thomson. They are real things.
Yeah, so whether
their masses have been measured, their charge has been measured accurately.
Mm-hmm. So essentially,
the positron too is a real thing.
Yeah.
Discovered by the, what do you call it?
Was it Anderson or something?
Anderson.
Yeah. What do you think of the neutrino, by the way? Musa, what do you think of the neutrino? Do you think that's real? Neutrino. This small neutral particle, which was postulated maybe first to balance the equations in beta decay.
Well,
a lot of people think that was a flood factor.
I cannot delve into that. But what I can say is that if you combine an electron and a positron, you form a neutral particle. They don't annihilate. They form a neutral particle, which is an essential component of matter.
I would argue that instead of marrying the electron to what we call a positron, I would argue it is simply the proton and the electron in my book, but that is a personal opinion, is what forms what we call the free neutron, meaning the neutral particle, right? And within the nucleus.
Exactly. Yes, I'll agree with that.
Right.
It's a question of name.
Say again, please.
Yes. They don't annihilate. They form a neutral particle. Whether you call it a neutron or a neutrino, we have not decided on a name yet, maybe. But if you think that an electron and a positron coming together annihilate, that is something. If they do, they don't annihilate.
Agreement with that annihilation.
Some other comments coming in now.
They don't annihilate. They form a neutral particle. You can call it a neutrino, or a neutron, or whatever. But the matter must be composed of electrons, positrons, and some neutral particles. There must be a neutral particle somewhere. Okay. If electron and positron annihilate, if they meet, that will not be here now. That will not have been creation. Creation comes simply because they don't annihilate. They form a neutral particle. And we haven't given it a name yet. Maybe neutron or something, a dipole.
Okay, if I may, I'll bring you down, Cornelis, for the moment, and also Ido, and we'll perhaps move on. Thank you very much for your contribution, and thank you, Musa, for
Thank you.
points, because we have limited time. Let me see now. Just have to get everything right now. And Ido, thank you indeed. There might be a moment to come back if you have something pressing. But you see, Jim Morrison has been talking about if mass is concentrated substrate, which we might call the ether, then the missing mass is due to conversion back to the substrate. So what's your view of the existence of maybe an ether, Musa?
Yes, that's been a big question. My view of the ether is that it's just an electric field. A neutral body composed of equal number of positive and negative charges has electric field in space, but the electric fields cancel. Simply because they cancel, it does not mean that they are not there.
Okay.
You see, so that's my idea of ether. It's an electric field medium where the electric fields cancel, but square of the electric fields do not cancel. As the square of a negative is positive. So as far as the electric field from bodies are concerned, the square of the electric fields remain in space to account for the mass and density and radiation, transmission of light in the ether. So a neutral body has its electric field extending to infinity, but reducing to zero. But at any other place, the electric fields cancel. But the square of the fields do not cancel to account for the mass density and energy density of the field. So ether is a reality, but we have not yet come to grasp as to what really it is.
Actually, the old green man, he says, the actual formula for the E equals mc squared is in the Einstein's 1905 paper, and he gives all this bit, it's L and so on, the beta factor and blah, 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 delta mc squared. But you probably reject his Einstein's derivation of that, Musa.
Apparently, I do.
Yeah,
yes.
Okay. Yeah. The other thing, I'm sorry I'm moving on a little because we may have a little more to do and we've very little time left. Carl Reef wrote to me some time ago saying that he wanted to put his hand up to make a contribution, but he tends not to have a camera, although he has a microphone. Can you hear me, Carl? You'd have to unmute yourself if you want to ask Musa a question. Well, there's nothing I can do then. If you want to come in, you can. Now, who's Tolga Yarman? Is that one of your colleagues, Musa?
What?
There's a gentleman, a person, I'm going to bring him up now.
Hello, I'm Professor Tolga Yarman.
Okay, you're very welcome. I just didn't recognize you.
Thank you so much.
Where are you based, Tolga?
I am in Istanbul, Turkey.
Okay, very good. Okay, well, you're very welcome. I just hadn't recognized the name. You possibly had been in before. Have you any question or any comment you'd like to make?
I just came in. I couldn't listen to anything. So congratulations, first of all, but I just came in, so I have to listen more.
Okay, well, I'll take the opportunity of saying while you're up just for a second now that most people know this, but as soon as we finish in 15 minutes, this will be available on YouTube. So you
Okay.
can look back, and I would recommend that all people do it, because even myself, I missed a couple of points. Maybe, although Musa was speaking very slowly and very clearly, but I'd recommend that. So if you have any comments you want to make at this or a later stage, Tolga, am I
Thank you
pronouncing
so
your
much.
name correctly, Tolga?
I just heard you very well, but I like to listen to the speaker a little bit more. I just came in, so I know what he's talking about, but I like to hear him a little bit more.
So may I just ask you?
Of course.
Would you classify yourself as a dissident physicist? You're not really mainstream. You're a bit like most of us here who would question the orthodox physics. Although you're an academic.
My academic, yes, indeed, and I'm not really a dissident. However, I have new ideas and new papers, original papers, new papers about gravity, and applicable to all bound fields. As a matter of fact, we made publications against the mainstream, really.
Okay, well, whether they're against mainstream or not, we're actually looking for people, critical thinkers, to talk to us on Saturday. So if you have any proposals later this year, maybe in the coming months, if you drop me a note, maybe making a proposal, we'd be very happy to have you give a talk at a later stage.
Okay. Can I communicate to you my email address, or just tell me your email address if you like?
Okay, it doesn't matter. I'll give you my you could write to the CNPS, but I'll give you my private email address.
Okay.
It's Ian Cowan, IANCOWAN.
Okay.
DR. Ian Cowan, DR.
Like doctor.
Doctor, yeah. At gmail.com.
At gmail.com.
At gmail.com. If you at your leisure want to propose anything to me,
my email address is very easy. It's Tolga Yarman.
Okay.
Tolga Yarman altogether.
Like me.
Tolga Yarman.
Yeah.
And at gmail.com.
Okay, even easier than mine. Okay.
It's even easier. So there is no doctor.
Actually, Ian Cowan was taken, so I had to put DR in.
Okay. What are you teaching, Ian?
I'm retired. I'm electronics engineer, physicist, mathematician. I've been working in industrial research and standards for 40 years, but I'm retired now, so I'm doing my own things. But I'm physics.
I'm a nuclear scientist. I'm a PhD from MIT Nuclear Science and Engineering Department.
Oh, are you? Okay.
MIT Nuclear Science and Engineering Department, long time ago, though.
Okay. That's very interesting, because I'm not as fundamentally involved in physics. My doctorate, I suppose, was more in mathematical modeling and computer simulation of thermal energy systems.
David Histler knows me very well. He knows me very well.
Okay, perfect. And forgive me for not knowing you, because I haven't been in this.
It's okay. Very long. I was for a long time away from this.
Okay. Well, we look forward to your participating in future conferences and maybe giving us a talk.
We published a new gravitational theory in Annals of Physics in 2023. So I will talk about that if you like.
Okay, that might be something to give a talk on. Thank you very much, Tolga.
Okay, great.
I'll bring it down now. Okay, well, we're coming quite close now, Musa. I haven't succeeded in getting James Keane. He's made a number of comments, and he normally likes to address those, but I think he's probably not available at the moment. He's been called away. But I think almost everybody who's come into the green room has spoken, apart from Carl Reef, and. We have your contact now, Musa, and certainly for my part, if I may say so, if people have any specific questions which they didn't get to address, if I'd be happy to forward them to Musa, and I'm sure Musa would be happy. Yeah,
that will be fine.
Thank you very much indeed. Yeah, because that's part of this. We've made a continuing introduction. we can deal. We won't be able to deal with everything in 2 hours. What does Cornelia say? Ian and Musa, thank you for letting me speak. It is clear that I know he's saying here. It is clear, Musa, that your views differ greatly from mine, as I accept complete energy mass conversion. What would make it difficult to discuss? Yeah, I know your views are like that, which is fair enough. We all have different views, and you can see that, Musa. I would be brave enough to say that most people participating would have a great degree of sympathy with your ideas, as I would, because they're very similar. We're all what we might call dissident scientists, but we're not people who would stop, censor any views. And we do have some people. I mentioned Kev, who's a very analytical mind, who tends to be more mainstream, and he's very welcome as well. So, okay. What does Green Man say about this equals empty square thing again? He said, if you want the rest mass, you have to add up the energy of a lot of photons to get something equivalent to it. I think SR has been misinterpreted, and maybe Einstein was a little confused. I don't know what you think about that, Musa. It's not only maybe, confused. Yeah, it's not only maybe that he said things that may not be agreeable to all, but maybe he's been misinterpreted.
Certainly, he will not only interpret. He was confused.
Yeah.
If you look at the amount of things that he said, like in relativity, length construction, time dilation, Einstein originated mass expansion. He originated it from the result of the Michelson-Morley experiment.
And even Lorentz, whose ideas he relied upon very much, I think, talked about this, where you didn't just add the two speeds, you had a modification. He said that cannot be accepted without a degree of skepticism. It might be necessary to comply with the transformations, the Voigt or Lorentz transformations, but it cannot be accepted without a degree of skepticism. Whereas Einstein just said it has to be accepted. And his followers would say, well, all these illogical things that are coming out of relativity and paradoxes, you just have to dismiss the logic from your mind and just accept them, because that's what the equations say. So, okay, well, let's see. We're coming near the end. I think we're going to have to wrap up. And what I normally do, Musa, unless just while I'm speaking now for the last few minutes, somebody comes in with a new question, I will put it up. What I normally do is I don't know. Denny says that Einstein was the modern Pied Piper of Hamilton. Yeah, I'm surprised. Yeah, okay, surprised at that. Anyway, he says actually that he, I don't know, because I might be speaking to Denny about this later. We didn't really have time to bring you in. Okay. Denny had difficulty. See, normally we have Denny up in the green. I wasn't able to enter the green room as you didn't send me a link. I apologize, Denny. My sincere apologies. You see, the link should be updated automatically, but some people's systems don't link that, and it was my fault. Roger didn't do it, but it was primarily my fault. I should have posted the link, so I'm sorry about that. It's probably too late to do it now. Well, wait a minute. Just before we summarize, better late than never. I've posted it now. So, Denny, if you do want to come in just for about 1 or 2 minutes, we might be able to take a brief very briefly. But pending that, I'll keep an eye out for you. What I normally do, Musa, is I give you a few minutes. Again, floor is entirely yours, and you may wish to summarize the situation. You may have other things you want to address very, very briefly in the light of the discussion or questions which have been raised. And you can speak for a minute, or you can speak for up to 5 minutes. And then I'll come back and officially close the meeting. So
Okay.
is that all right? Okay, so I'll just there you go, Dennis. I don't know if he wants there's anything left. Yeah, well, if Dennis manages to come in, James has come back, but it's too late. So I'm going to give you the floor again, Musa, to let you have the final word after your talk. So I'm
Okay.
disappearing now for a few minutes.
Yes, thank you very much, Ian, and all those who have asked questions. I have been very educated by this session. It's always a two-way affair. I still have to go back to Coulomb's law, which is one of the most important principles in physics. The problem of physics today is in making Coulomb's law independent of speed of a charged particle in an electric field. All the problems we have now in physics, lens construction, time dilation, and things like that, could be connected with that. Once you make Coulomb's law dependent on speed of a charged particle in an electric field, a lot of things come to light. Emission of radiation, speed of light is a limit. Even to the extent of having charged particles composing a body, if you have equal number of charges, all neutral bodies are made of equal numbers of combinations of electrons and positrons. The electrostatic forces of repulsion and attraction between the charges cancel out everywhere, but the gravitational forces remain in accordance with Newton's law. Any issue of gravity which does not produce Newton's law need to be re-examined, like general relativity. So the whole issue comes to electrons and positrons. Of course, some may even say they do not exist, or they are just waves in pursuit of wave-particle duality. But electrons and positrons are realities. We are aware of gamma rays, but we should also know that rays of positrons have been produced in the laboratory. Only that they had to be prevented from contact with any surface other than the intended cathode. So if you go round and round, we come back to this issue of electrons and positrons, and a combination of them forming neutral particles with matter as we know it. The whole issue really revolves around to explaining gravity. Such an important and all-powering force must have a simple explanation. And what we presented today should have presented such an explanation. This issue of quantum mechanics, general relativity, are just high-sounding stuff for the sake of teaching and examinations, but they don't conform with reality. In this paper, I gave an expression for the mass of an electron or positron in terms of the charge. And We use that to go back to gravity in terms of Newton's law. So all in all, I must say that we have to go back to the basics rather than now where we are in the wilderness of special relativity and in the quagmire of quantum mechanics. These high sounding dispensations are appealing, but whether they are correct or not, we need to re-examine them. And it all goes back to Coulomb's law and Newton's laws of motion. So, distinguished ladies and gentlemen, let's go back to the basics. Anything that does not appeal to reality must be re-examined. We have only one source of dependence, reality of the physical world. Anything that does not conform to it should be re-examined. Sometimes we may feel that maybe we are lacking in understanding or comprehending these complicated things. But anything that is too difficult or too complex to understand is probably wrong. You must have heard of some distinguished physicists saying nobody understands quantum mechanics. If nobody understands it, simply because it's not real. Reality is simple and beautiful, and that is what we are looking for. I thank all those who have attended this session for the wonderful opportunity to exchange ideas which I hope I will carry forward. I really thank Ellen Jr. for this opportunity. And a great thank you to all those who have attended this session. I have missed MPA for a long time, but now I will come back in full force and try to join such sessions. I traveled to USA, Canada for the MPA meetings when I was younger. I can't do it now. But doing it at home in an opportunity like that is most welcome. And I say a great thank you to all those who have attended this session. And I wish you safe journey back to wherever you came from. Thank you very much, Ian, for this opportunity.
Well, Musa, what can I say? Our thanks are actually due to you, because you've taken great trouble to present to us in 1 hour. You kept the hour, actually. I wasted some time at the beginning with administrative things, but you gave us the essentials of your papers. Your papers are very, very deep. I always respect a person who talks about things and then quantifies them. You know, one without the other is meaningless. Just putting equations down for the face, which have no relationship to reality, and then just talking and making statements without quantifying what you're talking about. Your papers are full of both. You have both. And as I said, I found them maybe a little taxing to read, but I enjoyed reading them. But I found your exposition very, very clear today. You're a very, very clear speaker. You're a slow speaker. I think you'd be a very good lecturer. You probably have actually a lot of experience in that in your earlier life. And you were certainly involved in the then NPA before I was. You attended, I think, the last face-to-face meeting that we had actually in Vancouver in Canada. So we're delighted to hear that you will renew your participation, and we hope to see you at the other at further sessions that we have, particularly on Saturdays. And indeed, I hereby invite you to consider coming back to us maybe later in the year and giving us another paper. we'd benefit very much therefrom. And it's also very heartening to hear that you're grateful to us in, if ever so small a way, because we want to pay back to our lecturers, people like you who've taken great trouble to explain to us the results of many, many years of deep thinking. We can see, as I said earlier, you're an analytical thinker, and we've had the benefit of your analysis. But if in promoting those ideas to us, a motley crew, most of us may be sympathetic, some of us not so sympathetic, but if you found that useful and you found it advantageous to your thinking to discuss some of your ideas with us, and indeed to have this as a permanent record of not only your lecture but of our reaction to it, well, we'll be more than happy that we've repaid you, if in only a very, very small way. So unfortunately the time has caught up with us. We must close the meeting now. Thank you very much for the people in the social media, Facebook and YouTube, for participating and all your questions. I think any specific questions I got to deal with, but if I missed anything, please feel free to come back to us and we can take these up again with Musa, who I think will be participating in the future. So we haven't seen the last of him by any chance. And also people in the green room, thank you very much for your participating, and also Tolga, whom I hadn't met before. So I hope we've only started something. We're not completing now. We've just started something which will bear further fruit later on. So I'm going to end the presentation now, as I must end the stream. I'll stay on for a minute or so, just in case there's any reaction from any of you that you didn't get to make. And I'll wish you, wherever you are in the world, whether you're in the Americas, whether you're in Europe, whether you're in Africa, wherever you are, whether you're in the Southern Hemisphere, a very good day. Thank you again.